minutes for AP Calculus on the topic of relative and absolute extrema. So let's review the first derivative test, and because you use the first derivative, remember this is where you find the first derivative, draw your number line, put down your critical numbers, where the derivative is 0 or undefined, and then test in those intervals. So if the first derivative is positive here, negative here, then positive here, then that would tell you that you have, at this point, since the first order changed from positive to negative, the graph goes from increasing to decreasing. This would be a relative or local maximum. And here, since the first order changes from negative to positive, it goes from decreasing to increasing. This would be a relative or local minimum. So that's the first order test. The most common way we use to find relative extrema, which means both relative minimums and relative maximums, and intervals where the first derivative is greater than 0, positive, indicate f is increasing. So here f of x increasing these intervals, and intervals on which the first derivative is less than 0, because the first derivative gives you the slope. If the slope is negative, like it is right here, function will be decreasing. And as we saw right here on the number line, if a derivative of a function changes from positive to negative, like it does right here, at a critical number, there's a relative, or sometimes it's referred to also as a local maximum. And assuming the function is continuous there, has to be connected there. And same thing if the derivative of a function changes from negative to positive, like it does right here, at a critical number, there's a relative or local minimum. At that critical number. Remember, critical numbers are where the first derivative is 0 or undefined. All right, let's take a look at some examples. We're using the first order test. So it says find the increasing and decreasing intervals of the function and find the coordinates of all the relative extrema, that means both relative and maxes, and identify each as a relative maximum or local. So let's start by finding the first derivative. And notice we've got x cubed divided by x squared minus 3, so that would be the quotient rule. So the first derivative, f prime of x, would equal the derivative of the numerator, derivative of x cubed, 3x squared, times the denominator as it is, 3, minus the numerator as it is, x cubed, times the derivative of the denominator, 2x, all divided by the denominator as it is squared. Alright, now we can simplify this a bit. If we distribute out the 3x squared, it gives us 3x to the fourth minus 9x squared. Simplify this, that's 2x to the fourth. The denominator is already in a factored form, so that's probably easier to just leave the way it is, not squared out. So squared minus 3 squared. Then we've got some like terms here. We've got 3x to the fourth minus 2x to the fourth. This gives you 1x to the fourth. So now we've got x to the fourth minus 9x squared. X squared minus 3 squared. And then you can take out the GCF of x squared on the numerator. And that was x squared minus 9. And then you can factor that with different squares. X squared, x minus 3. And then we can put our critical numbers on the number line. Well, first let's find them by saying the numerator equals 0 and the denominator equals 0. And the number line. So for the numerator, we've got 0, 3, and negative 3 to make the root of 0. What f prime of x. But then the denominator could be 0 as well. If you set x squared minus 3 equals 0 and add over the 3 and take the square root of both sides. And whenever you take the even root of both sides, remember you need plus or minus. So equal plus or minus square root. Square root of 3 is between 1 and 2, closer to 2. Square root of 4 is 2. So we'd have positive and negative square root of 3 as well. And those make the derivative undefined. And then we can start testing in between here to see if the first order is positive or negative. So notice we've got the squared here, so that'll never be negative. The squared here, so that'll never be negative. So really we just have to test them to x minus 3 and x plus 3. So if we test negative 4, that would make negative 4 minus 3 is negative, negative 4 plus 3 negative, negative times a negative is positive. There. Between negative 3 and negative root 3, that's negative 2, minus 3 is negative, negative 2 plus 3 is positive, negative times a positive is negative. Here you could test negative 1, minus 3 is negative, plus 3 is positive, still negative times a positive, still negative. Here you could test positive 1, minus 3 is negative, 1 plus 3 is positive, still negative. 2 minus 3 is negative, 2 minus plus 3 is positive, negative times a positive, still negative. And then 4 positive times a positive. So let's write down the increasing and decreasing intervals first. So based on the number line, you can see f is increasing on negative infinity to negative 3, and then u with 3 to infinity. Those are the intervals where the first order is positive. And then f is decreasing on negative, where the first order is negative, negative 3 to negative root 3. We do have to stop there since it's undefined. U, negative root 3. You can stop here at 0, but you don't have to because it's 0 not undefined, so you could go all the way to positive root 3. U, and the final one is positive root 3. And then we can see based on our number line here that negative 3, the first order changes from positive to negative. So that's a relative max. And at positive 3, the first order changes from negative to positive, goes from decrease to increase, so that's the relative. And here it said find the coordinates. So we have to find the coordinates of each of them. So let's find, on the y coordinate, we have the x coordinate, back to the original equation. So f of negative 3 divided by negative 3 squared minus 3. Negative 3 cubed is negative 27 over over negative 3 squared is 9 minus 3 gives you 6. Divide by 3 reduces to negative 9 over 2. So you can say as a relative maximum at the point negative 3, negative 9 halves. And then we can do the same thing with positive 3. See it's white coordinate there where we have a relative minimum. 3 cubed divided by 3 squared minus 3 is 27 over 9 minus 36. So the positive things. So it's F as a relative minimum at positive 3, positive 9. All right, let's take a look at another example here. This one a little more complicated. But here it just says find, we're not finding quite as much information. Find the x coordinate of each local minimum and local maximum and justify your answer. Each intervals, even though we're going to find them. So the first thing I would do on this is rewrite it so it's easier to take the derivative of. So we've got x, and then we've got 9 minus 2x. Rewrite it. And overall, we're going to use the product rule, where it's x times. Oops. X is your first one, and then 9 minus 2x to the 1/2 is the second one. So using the product rule, g prime of x would be the derivative. Derivative of x is 1. And the second one, 9 minus 2x to the 1/2 as it is. Plus, first one as it is, x. 9 9 times the derivative inside, which is negative 2. And to simplify this, as we go about it, one of the most efficient way is to minus 2x to the 1/2 and negative 1. So let's factor that out of the PCF. And use it to the lower exponent, the negative 1/2. And look like, well, what's going to be left here is 9 minus 2x. And the exponents have to add up to be 1/2, so it has to be a positive 1. Positive 1 and negative 1/2 add up to be positive 1. And then I'm going to bring this negative from right here out in front. Notice the 2's reduced out. So all we're left with, and this we completely factor out to the negative 1/2, so all we're left with is x. Then we can simplify it a little further. Moving to the denominator, put it in radical form. And then we've got 9 minus 2x minus another x gives you 9 minus 3x. And you can factor that a little further. 3 3 times 3 minus x divided by the square root of 1 minus x. And then now we have simplify, we can find out numbers by saying denominator equals 0. And let's draw our number line. 3 from the numerator. And if you set 9 minus 2x equal to 0, you would add the 2x over and divide by 2, so you get 9 halves. Those would be our two critical numbers. This came from the numerator 0, 9 halves came from the numbers undefined. And then we can test. If we test 2, that'd be a negative. 3 minus 2 is negative, over 2 in there would be positive. Negative divided by positive is negative. Oh, and don't forget to label in front of x. And then here between 9 halves is 4 1/2, so between 3 and 4 1/2 we can test 4. 3 minus 4 is negative. And if you put 4 here, oops, I made a mistake on the other interval, sorry about that. I just noticed, if I test 2, 3 minus 2 is positive over positive, so this one's actually positive. I noticed that because when I tested 4, I was getting the same thing here. So 3 minus 4, that's negative, over 9 minus 8, that's positive. Positive, negative. And then here you test 5, that'll be a negative on the numerator, over negative. In this case, 5 makes it negative and it's inside the even root, so it actually does make a mistake. So 9 halves is nothing because the graph just stops there. Everything else outside is imaginary. But 3, we've got a relative max. So we can say G, just ask for the x coordinate here, has a local maximum at x equals 3. G prime of x changes positive to negative. And if it was a local minimum, you would justify it the same way. It would just be since G prime of x changes from negative to positive at x equals 3. All right, let's take a look at a piecewise function now. So for a piecewise function, first thing we have to do is look at the breakpoints. Because the breakpoints are always critical numbers. They're always going to go on an underlying regardless. What we need to figure out to see if they could be relative mins or maxes is if they're continuous or not. Notice here it's got breakpoints of -1 and 3. So we can find the limit as x approaches -1 from the left using this top piece here. So that's -1 3 squared, give you 2 squared, which is, and compare that with the limit approaches -1 on the right. So you 2 plus 2, 2 plus 2, 4. So these are equal. So now we know this is continuous. It could be a local minimum or a local max potentially. Now let's compare our other breakpoint of 3 on a limit. So 3 from the left will be -2 times 3 plus 2 would give you -6 plus 2, -4. And let's compare that with the limit approaches 3 from the right. That would be -3 cubed, 12 times 3 squared, -27, plus 108. So here, they're not the same. So this is not continuous at x equals 3. Again, the importance of that is that means 3 cannot be a relative or max because it's not connected. All right, then we just take the derivative of each piece separately. In this case, we've got 3 pieces. So the first piece, the derivative would be 2 to the power plus 3 to the first. You technically use the chain rule here, but the derivative inside is just 1, so that doesn't change. We got the word 4 on all these here. So it should be 4. The second piece, the derivative would just be -2, just a constant. 4. Now, so I'm taking off the or equal to because most likely these, even though they're connected here and continuous, most likely it's not going to be a corner. You can tell real quick by plugging in -1, and you'll see you get 2 times 2 is 4 versus -2. So they're not equal, the derivative of -1. So even though it's continuous, you've got a corner there. So that wouldn't exist there. So I took off equal to this. And then the last piece, -3x squared plus 24x. For the interval here, you would take off the equal to because you know for sure the derivative doesn't exist there because it's not even continuous. Okay, now we already know our breakpoints -1 and 3 have to be on our number line because it changes to a different function. Now we want to see if we have any others by studying each piece of the derivative equal to 0. In this case, there's no denominator, so you don't have to worry about undefined. If this piece equals 0, we get x equals -3. And then just double check it's actually on that interval. Is -3 on less than -1 right here? It is. So that it would be a valid critical number. You would use that piece for negative. Now the middle piece, that's -2. That'll never be 0. That's just a constant. And if we set the bottom piece, x squared plus 24x equal to 0. Factor out -3. Put x minus 8. And you get x equals 0. But again, let's check here. 0 for this bottom piece is not greater than 3, so you would never use 0 here. 8, however, is greater than 3, so you would use that one. So now let's draw our number line. We've got -3 and 8, and to -1 and 3, our initial critical number from the breakpoint. That's how to do it. We've got 8, 3, -1, and -3 are our critical numbers. -3 and 8 both made derivative 0. -1 and 3. -3 is definitely undefined or doesn't exist. There's not continuous there. -1, we found a way to corner there, so that also doesn't matter on your interval here if you put things in. Okay, now let's test. So just make sure when you're testing your derivative, you use the correct piece. So here the piece for -4 would be less than -1, so -4 plus 3 is negative, times 2 is negative. Here you could test -2, which fits in the same interval. -2 plus 3 is positive, times 2 is positive. And here you could test 0, but 0 use the middle piece, and no matter what we test there, we're going to get a -2. That piece is negative. Here you could test 4, and it's funny to use the factored form down here of this third piece. So that would give you a negative there, -3 times 4 is 4 minus 8 is negative, so negative times a negative is positive there. And 9, negative times positive, negative. And then based on that, we can answer what it asks for are the increasing and decreasing intervals, and the x coordinates of all local extrema, and identifies a local max or local. And here's where it's important to indicate continuous. So at -1, that was continuous, but at 3 it was not. So let's write increasing decreasing intervals first. F increasing on -3 and -1, and U from 3 to 8. F is decreasing on -8 and -3. -3 and 8 to infinity. And finally, identify local mins and maxes. So at -3, first row goes from negative to positive, that's a relative minimum. 1 goes from positive to negative, and it's continuous, so that's a relative max. At 3, it looks like a relative minimum, but it can't be because we know it's not continuous, it's not even connected there. And 8 is a relative max. So, say, as a relative, or so called same thing, local maximum. Here it only asks for the x coordinates. At x equals -1 and x equals 8. And the local minimum. Oops, I spelled that wrong. At x equals -3. Okay, let's transition to absolute minimum and maximums. Similar concept to relative mins and maxes. Relative mins and maxes just means relative to the points on either side, not necessarily the entire function. Absolute minimum maxes is talking about the entire function. Still look at relative mins and maxes, but you also have to consider the endpoints. So we start off the same way. Take the first derivative. The 2x minus 8x. In this case, there's no place this is undefined, no denominator. So we just see what makes it equal to 0. You can see up to 2x, and you and that factors further. Squares. So we get our critical numbers here are from the 2x, we get 0. From the x minus 2, you get 2. And from the x plus 2, you get 0. However, on these absolute minimum maximum problems, or absolute extrema, what would be called the other, you're given usually an interval. We're looking from -3 to 1, and notice +2 is not in that interval. So for our purposes, that's irrelevant. So we'll just use -2 and 0. And then we can draw our number line. And this time we've got endpoints on our number line, so we'll put first. Got -3 here, and 1 here. And then we'll have -2 and 0. And then we'll have this f prime of x. The -2 and 0 both make the first derivative 0. And then when you're testing, you actually can test this endpoint at -3 if you want, because it's not a critical number. So -3 would make this first one negative. -3 minus 2 negative. -3 plus 2 negative. 3 negatives multiplied together is negative. Here, between negative 2 and 0, you can test negative 1 times 2 is negative, negative 1 minus 2 is negative, negative 1 plus 2 is positive, 2 negatives times a positive would be positive. And here you can test 1 because it's not a critical number. 1 times 2 is 2. 1 minus 2 negative, 1 plus 2 positive. 2 positive times negative is negative. So this shows us that f of x, the first row is negative, would be decreasing, positive, increasing, negative, decreasing. And here's helpful to actually sketch a little graph because we're only looking for that for the maximum. So you can sketch, okay, we know decreasing, then increasing, and then decreasing. And based on that sketch, you can tell the maximum can only occur either at our relative maximum here at 0 or at the endpoint of negative 3. It's got to be one of those points. The negative 2 and 1 would be the potential absolute minimums if we were asked about that. So we just have to compare which one of those two is greater. And you have to compare them in the original function. So let's compare f of negative 3 with f of 0. F of negative 3 would be 1/2 f of negative 3 to the 4th. Okay, so negative 3 to the 4th is 81 times a half, so 81 halves minus negative 3 squared is 9 times 4 is 36, but we want it as halves. So that is the same as 72 halves, and 9 halves. And we're trying to find the maximum value. So let's compare that with 0. Well, if we plug in 0, you can see what's going to happen. 0 is going to wipe everything out, giving you 0. And you can see 9 halves is greater than 0. So that is our maximum value there. But it says on the given interval and justify your answer. So you can say you can say absolute maximum or just maximum either way. Okay, maximum value of 9 halves. And it's good to specify where that occurs at so you can justify it. At -3. And then to justify it, since you can really just specify the ones you compared, since f of negative 3 is greater than x. As long as you're drawing your number line to show your analysis there, then you can use that as your justification. All right, so that one we're looking for an absolute maximum. Now let's take a look at one we're looking for an absolute minimum. Okay. Another piecewise function. So again, let's start off by figuring out the function's continuous at the breakpoint. In this case, there's just one breakpoint of 2. So the limit as x approaches 2 from the left. X will be 2 cubed minus 27 times 2 gives you 8. 2 cubed minus 54, negative 46. And then we have to compare this on the right. Limit as x approaches 2 from the right. That would be 5 times 2, 6, 10 minus 56 gives you negative 46. So they do meet up. It is continuous. That means that our breakpoint is going to be on a critical number for sure. 2 could be a relative minimum or a relative maximum. And here's our interval, negative 4 to 4. So again, let's take the derivative of each piece and see if there's any more critical numbers besides the breakpoint that we use. So the derivative of the top piece would be 3x squared, 27. Sorry, I forgot the word 4 there. 4x is less than 2. And the derivative of the bottom piece would be just 5. Again, I'm taking out the equal to sign because even though it's continuous, it's not going to be differential because if we substitute in 2 here, so we get 2 squared is 4 times 3 is 12 minus 27 is negative 15, not 5. Those aren't equal, so definitely not a corner there at 2. The derivative doesn't exist. All right, now let's see if we have any other critical numbers. Let's see 3x squared minus 7 equal to 0. And then you can factor out a 3, BCF, and then that factors further into x minus 3x plus. And in this case, both of those, 3 and negative 3, are divisible from negative 4 to 4. However, we also have to look right here. And see, we'd only use these for this piece where x is less than 2. Negative 3 is less than 2, but not positive 3. Cross off positive 3 and not in there. So you never plug 3 into this piece anyway. All right, now we can draw our number line. Endpoints here are negative 4 and 4. And we've got negative 3 as a critical number, and our breakpoint. You can always label it. Negative 3 came from setting the derivative equal to 0, so that makes the derivative 2 made it undefined here, or doesn't exist. All right, so here we could test negative 4. And if you test in this factor form, it's probably a little easier. The 3 is always positive. Negative 4 minus 3 is negative. Negative 4 plus 3, negative. Negative times a negative. So you could test 0. 0 minus 3 is negative. 0 plus 3 is positive. Negative times a positive is negative. So you could test 3 or 4. But here, be careful because you wouldn't be testing in this piece because now you're beyond greater than 2, so you have to test it here, and it's always positive 5 no matter what you test. So here, you can see f of x increasing, decreasing, and increasing. So if we sketch a little graph of it this time, increasing, decreasing, increasing, and we're looking for the absolute minimum this time. This time you can see the minimum could be either at negative 4 our endpoint or at positive 2 our relative. Compare those two and see this time, since we're looking for the minimum, we're looking for which one is small. F of negative 4. So for negative 4, you would use this top piece here. So you'd have negative 4 cubed, because it's less than 2. 27 times negative 4. Well, negative 4 cubed is negative 64. 4 times 27 is 108, and the negatives cancel out. And that gives you 44. And we're looking for the lower value, remember? That's the minimum. And let's compare that with 2. Now you could find it again, but remember we already plugged in 2 into this function, and we got negative 46. So that's definitely the lower of the 2. So we can say the minimum value F is negative 46. X equals 2. And then your reason, since, well, you've drawn the number line, so into your analysis, that since f of 2 is less than f of 8, because those are the two possible places it could have been. All right, let's go one more, and this one, let's try one with a trig function here. And this one we're asked for the absolute minimum and the maximum as well, and to justify our answers. So let's start by taking the derivative. X is 1, or sine is cosine, the negative 3 just stays out in front. And then we set that equal to 0 to find our critical numbers. Here you can add the 2 cosine x over here, and then divide by 2, And then we can see what this will work. Cosine x is, and we can draw this. Remember, we're just looking from 0 to pi here. And cosine, remember, is the adjacent over the hypotenuse. So if we look on the unit circle here, see it's positive, cosine is positive. Here's 0 right here. And here's pi. So the only quadrant cosine is positive there is in the first quadrant. Adjacent is 1. Hypotenuse is 2. This side would be root 3. So you can see that angle is pi over 3. That's it. This time we only have one critical number of x equals pi over 3 in the interval. Draw our number line now. So we've got pi over 3. 0 to pi. And when we prime of x, and pi over 3 makes the first root of 0. Here you could actually test 0 in the derivative. Make sure you don't test it right here, but right in the first derivative itself right here. Cosine of 0 is 1, so that would be 1 minus 2 would be negative. Okay, you could test pi. Cosine of pi is negative 1, that would make that a plus 2. And plus 2 is positive. So this time it's a little simpler. It's just going to, the f of x graph, if we sketch it, and decreasing. Okay. So that's for both maximum and minimum. So let's start with the maximum here. So the maximum could be at 0 or at pi, one of the inputs. So we have to compare those two. So compare f of 0 with f of pi. Largest if we're looking for the maximum. So f of 0, you would have 0 minus 2 times the sine of 0. Sine of 0 is 0, so that would just be 0. F of pi, pi minus 2 times the sine of pi. Sine of pi is 0, so that works it out, but we're still left with pi, so pi would be our. So we can take that one first. Maximum value is pi, and it occurs at x equals pi. That would be the same here. And then to justify it'd be since f of pi squared. And then for the minimum value here, we can see it's got there's only one place it could be. It has to be right here. But we still need the values, so we really know where it's going to occur at. Absolute minimum. That would be f of pi over 3. Well, that would be pi over 3 minus 2 times the sine of pi over 3. We already have pi over 3 drawn here, so we can see that pi over 3 minus 2 times the sine of pi over 3, opposite over hypotenuse, root 3 over 2. And then you can see the 2 reduce out. So we just end up getting pi over 3. That's our minimum value. There's no other place it could be at. Based on our number line there. So we can say finally, justification is just a little different on this one. The maximum, or sorry, the minimum value is pi over 3 minus root 3 at x equals pi over 3. And here you're not comparing this to anything, so you can just use the same justification you would use for a relative minimum. Since f prime of x changes from negative to positive at x equals pi over 3. And you can add on also, because normally consider the endpoints too, neither endpoint is a potential maximum. Just circle the answers here. There's our maximum value with justification, and there's our minimum value with justification. And that concludes the notes for AP Calculus on the topics of absolute and relative extrema.